Hello, my name is Ben Steppers and I'm from the University of Manchester in the UK. And today I want to tell you something about radio pulsars and pulsar searching. So these exotic objects called pulsars and how we would go about finding them. To start off with, we need to consider stars as they are the progenitors of the objects that we're interested in. On the right-hand side, you can see something called a Hertzsprung-Russell diagram. It shows how stars evolve, and it shows how the speed at which they evolve depends on their mass. And you can see for stars of around about 9 and 15 solar masses that they evolve incredibly rapidly by comparison to these very low mass stars. And it's these stars that we are particularly interested in when we're talking about pulsars. Pulsars are a type of rotating neutron star. So how do we get a neutron star? Well, it turns out that as these stars of around about 9 solar masses and above, as they evolve, they burn through different elements. They burn through hydrogen and helium, so they're fusing hydrogen and helium, and that fusion process generates energy. And that energy is what powers the star and also supports the star so that it doesn't collapse under its own weight. However, eventually the stars start to form iron in their cores. And when that occurs, it reaches a point at which if you were trying to fuse iron elements together, you'd need to supply energy rather than when you're fusing hydrogen and helium, which releases energy. And so what that means is that there's no source of energy or radiation in the center of the star to support the mass of the gas that is unburnt, that is above this iron core. And so eventually what happens is the star starts to collapse. And this collapse results in the squeezing of the material right in the center of the star. And when the pressure gets to a certain level, the material bounces, and that bounce produces this explosion that we know as a supernova. And what you can see here in this video is that that gas and material eventually is blown out into space and leaves something called a supernova remnant. However, the object that we're most interested in today is the neutron star that is formed in the middle. And that incredible pressure as the material falls in is what's really key here. It compresses the material of the star so much that electrons and protons start to fuse together, and we're left with a star which is predominantly made out of neutrons. The mass of these objects is around about 1.4 solar masses. So of those 9 to 20 solar masses that we started with, around about 1.4 solar masses is left. But incredibly, that's all squeezed into a radius of just 10 kilometers. The supernova remnants, which you can see in the right-hand side here, it's an X-ray image actually taken with the Chandra Space Telescope. They usually last for something around 20,000 to 100,000 years. So if you find a pulsar located inside a supernova remnant, then you've got a pretty good idea that it's a young pulsar. So I mentioned about this 1.4 solar masses squeezed into a radius of around about 10 or 20 kilometers. And what that means is that if you could somehow get hold of a teaspoonful of neutron star material, then it would weigh as much as 1 billion elephants. Okay, so the density of this material, this neutron star, is incredible. And is something that just cannot be recreated here on Earth. Now, what makes a neutron star a pulsar is very interesting, and we'll get to that in a moment. But what we can see here in the right-hand side is a graphic which shows you some of the exotic physics that is associated with these extremely dense objects. We think that the outer layer is a crust, and on the very outer layer, there is actually also a very thin atmosphere, which might be a hydrogen or helium style atmosphere. And then just inside the crust, we actually have what we call the core region. And in that core region, we think that we have a neutron superfluid. Okay, so this is you're possibly familiar with superfluids such as helium or other superfluids, and they have these amazing properties of that are really important when it comes to understanding the interiors of these neutron stars. So if we can study the neutron stars, then we might be able to study the internal physics, which again is something that cannot be recreated in laboratories here on Earth. So about what makes a neutron star a pulsar? Well, a neutron star that is spinning very rapidly and has a strong magnetic field and is giving off radiation from that magnetic field, like in the radio or the gamma rays or other wavelengths, that's what we call a pulsar. Okay, so that is, we'll show you some cartoons in a moment whereby we see that if this neutron star has a strong magnetic field and is spinning, then as the neutron star spins, then we will get what is called a pulse of radiation, and hence where the name pulsar comes from. Now, pulsars can spin with periods anywhere between 1.3 and, actually I need to update this slide. It's actually now up to 23 seconds. Okay, so they can spin up to 700 times a second or once every 23 seconds or so. They also have incredibly strong magnetic fields, something like 10 to the 8 to 10 to the 14 Gauss, or if you're more familiar with Tesla, something like 10 to the 4 to 10 to the 10 Tesla. They're predominantly radio sources. So the vast majority of pulsars that we know about, and we know about around about 3,000 pulsars so far, and the vast majority emit in radio or are only detected in radio. But they do also emit gamma rays, X-rays, and also some are known to be optical emitters. And the emission is typically in a narrow beam, and we'll come back to this point about clock-like stability. So here is a little cartoon again that shows you what we think these pulsars might look like. What we have is this very small dot right in the center here is the neutron star, and there's a little bit of a zoom in on that in the right-hand side here. And surrounding the neutron star is its magnetic field. Okay, so the magnetic field is basically like a dipole magnetic field, and you could see there are two important regions here. One is this so-called closed field line region, and then we have these open magnetic fields. The closed field line region is defined by the edges where if the magnetic field was going to rotate with the pulsar, then it would have to rotate with a velocity which was greater than the speed of light. Okay, so that is a boundary that cannot be exceeded. So the magnetic field cannot close if it goes back around outside of that velocity of light cylinder that we have. And so then we have these open magnetic field lines, and it's those that define the region from which we think the radio emission comes from. Okay, so that's how we get these poles, magnetic poles like a north and south pole, similar to what we have for the Earth. And from those poles, we get the radiation that we observe. And then when those poles sweep by us like a lighthouse, we get a pulse of radio emission. So how do these objects get this rapid spin? Well, pulsars can be born spinning up to once every 30 milliseconds. Okay, so they can rotate up to 30 times a second when they're born. And the ballet dancer that you can see here in this little animation is showing you how we get these rapid spin rates. What we have is, remember, we started with a star, maybe 9, 10 solar masses, maybe more, and it's going to be enormous. It's going to have a radius which extends right out past Jupiter in our own solar system. And it's probably spinning a few times a year or maybe once a month. So it's got a relatively low spin period. However, if we take something that is very large like that, and we shrink it down to the size of just a kilometer, just 10 kilometers or so, then because of conservation of angular momentum, the star must spin up. Okay, and so what you can see here in the animation, of course, is that the ballet dancer starts with their arms out wide, and they're spinning relatively slowly. But when they bring their arms in, they change their radius, and so they spin more rapidly. And that's exactly what's happening when neutron stars form from the supernova of these massive stars. It turns out that we can get pulsars that spin even faster. So as we showed, they can go down to something like 1.3 milliseconds for the rotation period. So how does that happen? Well, if the neutron star and the pulsar is lucky enough to be in orbit with another star, then after a while, the other star evolves. As it evolves, it gets larger, its radius increases. And when its radius increases, then material which is gravitationally attracted to the star is no longer preferentially attracted to the star, but would rather be gravitationally bound to the pulsar. And so it falls from the star, as shown here in the animation, down into a region we call an accretion disk. And this accretion disk is then able to transfer material onto the pulsar. And that transfer of material spins the star up. So the pulsar is spun up. It's again the angular momentum thing where the orbital angular momentum of the material that was traveling with the star is transferred onto the pulsar. And then you could see in the animation there that at one stage these beams, which are now shown in magenta, were a white color. And that's because that's when we get strong X-ray emission. So the material is being accreted, so falling onto the neutron star. The material falling on the neutron star gets hot. Hot material generates X-rays. And so that's why we see it as an X-ray source in that period. And then what we're left with is the pulsar now on the left-hand side, spinning much more rapidly. So maybe up to a few hundred times every second. And on the right-hand side, we are left with a white dwarf. This is a so-called low mass X-ray binary. However, it is also possible that we will end up with another neutron star. So one pulsar, one neutron star. And we'll talk about such systems a little bit later on and how they are very useful for testing Einstein's theory of general relativity. So here, just in cartoon form, we can see our little spinning neutron star, and it's got two beams of radiation coming from the magnetic poles. And as that object rotates, and if its beam crosses our line of sight, then we'll detect a pulse of radiation. Now, it's not the case that all pulsars will be visible from Earth, because you can imagine that there are situations where those beams actually will rotate like this, for example, if I am the telescope. And so then you'll never see a pulse. And so we think that maybe anywhere up to 50% of pulsars are not beamed in our direction. So there are more pulsars than we can possibly ever see with our radio telescopes. So just to summarize, we've got this remnant of a supernova at the end of the life of a massive star. We end up with these rotating neutron stars. They have masses of 1.4 solar masses, 1.4 times the mass of our sun. They have radius of 10 kilometers, periods of around about 1.3 milliseconds down to around about 23 seconds. They have these very strong magnetic fields. They emit across the electromagnetic spectrum, but are predominantly emitting in the radio. And they emit in a narrow beam. And the magnetic field strength that I mentioned, something like 10 to the 8 to 10 to the 14 Gauss, can be compared to the strongest magnetic fields that we know about, say, or common magnetic fields we know about, which are the magnetic field of the Earth, which is around about half a Gauss, or a bar magnet, which has a magnetic field strength of around 100 Gauss. So you might have used one of these bar magnets in experiments in class or at university, for example. It turns out that we can turn the signals that we received from pulsars. In some cases, they are strong enough that we can turn them into a sound. This is not how we analyze the data, but this is just to give you an idea of what these objects might sound like if we could play the sounds. So this is one of the brightest pulsars in the northern sky, and you can see it has a pulse period of around about 0.7 seconds or 84 revolutions per minute. And you can hear the pulse, pulse, pulse. And now we are listening to a pulsar that rotates 674 revolutions per minute. So that's similar to a drill, for example, that you might use to drill into the wall. And so you can hear and so now let's listen to pulsar B0531 plus 21, sometimes known as the crab pulsar. And it spins at 1800 revolutions per minute. Oh, it looks like that didn't work. Apologies for that. We'll try and play that for you some other time. So what do the signals look like that we get from these data? So I've shown you a sound, but now what does the signal actually look like? So here is a combination of the sound of this pulsar plus this radio signal that we receive. So here on the bottom axis, I'll plot time, and then I'll plot the intensity of the signal. And you can hear. So you can see these pulses now arriving every 0.71 seconds. And you can see also that they vary a lot in their shape and in their intensity. This is a common thing for pulsars, that they often look very different from one pulse to the next. But as we'll show you later, crucially, if I average, say, maybe a couple of hundred of these pulses together, I'll get a pulse shape which is stable over many, many, many years. And that is crucial for using these pulsars as cosmic clocks. The other thing you can see when you look at these arriving, you can think of this as like the ticks of a clock. Every time the pulse arrives, tick, 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 tick. And because these objects are extremely dense, it's very difficult to change the rate at which they spin. And therefore, we are able to use these as very precise clocks to do all sorts of tests of theories of gravity, but also for understanding the neutron stars themselves. So what is this radio emission? How is it generated? It's fair to say that we really still don't know. So it's more than 50 years since the discovery of pulsars, but the way in which they generate their radio emission is not well understood. We have a basic model, and that's what's demonstrated here, but we don't know in detail. What you can see on the left-hand side is the surface of a neutron star. This is not to scale, by the way, it's a cartoon. And you can see those closed field lines that I was showing you here, and then the edge of the light cylinder. And then at the magnetic pole, which is shown in this box region here, we have these open field lines. And then right at the top, we have the rotation axis. Now, if we zoom into this box, we think that the magnetic field strength is strong enough that it generates an electric field, and that electric field is able to set up a potential, and that potential is strong enough to pull particles from the surface of the neutron star. And what happens is that those particles are moving So you can see the charged particle here shown as this little circle is moving, and a moving particle on a magnetic field line, on a curved magnetic field line, is going to radiate. And so you can see it will give off a gamma ray photon. This gamma ray photon then splits into an electron and a positron. You can see that they move in opposite directions in the magnetic field. And then they are still moving, and then they in turn will generate more gamma ray photons. And what we say happens is we get a cascade. So we get lots and lots of these events happening at the same time. And then eventually this gamma ray, these electrons start to radiate at radio wavelengths. They no longer form the gamma ray photons that split anymore. And so we get radio waves, and then these radio waves propagate to us on Earth and are detected as the pulses of radio emission. So these are the basic ideas. There's a lot of uncertainty about the specifics of the physics involved here. Okay, I think that's a good place for us to pause. We will come back to talking about the pulse phenomenology after a short break for either questions or a drink.